find over the years that if you initial data and the initial data satisfies the constraint equations, then I can find what's called a globally hyperbolic development. And one can draw this like this. And this has the property, let me change the thickness of my pen here. And then one can foliate this region with slices like this. And this has the property that when I zoom in, let's say, and I take an arbitrary point here and I consider the path light cone of this point, then it has the property that all the time light curves emanating from this point register on the initial data. And this is why this line is drawn like this and not a straight line, because then you could have curves that do this and don't intersect the data. So that's why that's interesting. It's because everything that ever happened at point P must have registered somewhere on some Cauchy surface. And that's why we call it a Cauchy surface. Okay, good. And the space-time takes a particularly nice form. It's called globally hyperbolic when it has this property, and it just looks like a product. So the space-time is diffeomorphic to, forgive me, R cross V. So that just means V is the topology of the Cauchy surface, and the metric looks something like the following. So you have some factor which tells you how it's varying in time, and then you have some metric which is also varying in time and in space, of course, where H is induced on the manifold V, V being kind of a space-like Riemannian manifold. Good. So this is the preamble, right? But of course, famously, there are, well, you're all familiar, of course, with the Schwarzschild solution, or its maximal analytic extension, which looks like this. And in that case, there's an initial data here that I've just drawn. Let me use a different color. And this has a very nice property that it's a Cauchy surface for the space-time. So we are very happy here. But then, of course, there is something else, Rice and Nordstrom or Kerr, other types of solutions, which have been the subject of a mini-series in the foundation seminar, but which have the property that when you consider their maximal analytic extension, what you produce is something like the following, right? And if I draw an analogous initial data surface here, then you will recognize this region here. That's a little too thick. Let's change. Okay, this region here is now a boundary, which has the property that if I take a point here, right? If I take a point here and I consider the path light cone of this point, then the curves, right? There are curves which miss the initial data surface, right? Because they go in this region. And so here we are, of course, a frowny face. Okay, because we have a Cauchy horizon. And so, of course, this is an exact solution, and it's a great big open problem to understand. Suppose we take this kind of initial data, but we don't have exactly such initial data. We perturb it by something. So we add a perturbation here. Then do these go away? Do these go away? And do they end up looking more like this one, right? Where initial data is just enough to specify the whole space-time. So that's basically strong cosmic censorship in a nutshell. Whatever talk or whatever thing, it can all be summarized to this picture. I don't think we need to go any further, really. So if you've ever wondered about what it is, this is just it, really. Now, of course, we now go into some more specific history. So this picture, of course, was known, and then Roger Penrose and amongst other people tried to come up with a reason as to why these Cauchy horizons should disappear. And he had some students working on this, and what they did is they took Rice and Nordstrom
and they sent in some, and they try to understand how the scalar field behaves in the Rice-Nordstrom solution. The Rice-Nordstrom solution also has a Cauchy horizon, and they saw that in some linearized sense, in some perturbation, approximation, et cetera, they found that there was a kind of blow-up behavior along the Cauchy horizon. And the idea was that if there's a blow-up behavior, that means that somehow something's unstable is happening at the Cauchy horizon. And so in fact, these horizons should disappear in the generic case, and generic being in the realistic sort of initial data, not one that's exactly like the Kerr data, which is of course axisymmetric and stationary and all the rest of the beautiful symmetries that we know and love about Kerr. And so, Penrose supposes this. He says, okay, well, physically reasonable spacetimes ought to be globally hyperbolic. These Cauchy horizons ought to be unstable. Fair enough. And Garrosh-Horowitz, in a lovely article on global structure in '79, in the same volume, by the way, as the paper that has the origin of strong cosmic censorship. So I hardly recommend that volume, Hawking-Israel volume. Other contributions by lots of other people, which is really truly wonderful volume. Anyway, they put forward a kind of Lorentzian geometric statement that's supposed to capture some of the essence and spirit of strong cosmic censorship. And what they come up with is then picked up by Robert Wald in the writing of his 1984 landmark book, chapter 12, his version of strong cosmic censorship, where essentially they do not, it's very hard to come up with a precise mathematical statement instantiating Penrose's idea. And so what they come up with is a kind of intermediate statement, if you will, that's in the spirit of strong cosmic censorship, but that's not actually mathematically, the most precise rendition you could have of the Penrose intuition, which by the way was an intuition, not a conjecture. And they come up with this statement, right? And the statement says, suppose you have complete initial data, okay? So much like what we saw before. Suppose there's a Cauchy horizon. Suppose you take a point on the Cauchy horizon, then either two things must happen. Either there's a failure of strong causality at P, or the past of P intersected with the initial data is non-compact. Now, the relevance of the non-compactness is the following thing. And for this, you will have to permit me a fun analogy that will work out together. This is the Cauchy horizon. This is the initial data. Okay. Now, an observer out here, let's draw him or her with a blue line. Right. Suppose, for the sake of personal sacrifice, suppose I am sent off my spaceship into the black hole. Suppose this is me. And suppose this is the BHI team that launched a rocket, right? And that decided that, I was going to be flying as an experimentalist, which I am, of course. It's a huge joke, of course. I was going to be sent to do some, data gathering inside the black hole, knowing full well I wouldn't be able to come back, and it's the way it is. So I'm a sad, unhappy at this point, but well, I'm excited, but eventually unhappy. Anyway, I get to the Cauchy horizon, and my proper time here is maybe like, say, 4 hours or something, 4 hours, whatever. But the BHI team, hoping that perhaps there would be a wormhole that I could escape, but of course there isn't. They send me emails, say, well, where are you? Send me emails, right? Emails being sent. And of course, the proper time that they spend, supposing we can all live forever, is of course infinite, right? So what's going on? I'm getting infinitely many emails in 4 hours, right? I don't know if you've ever been in that situation. I think we've all had that feeling. So what's going on, right? What's going on? What's going on is that the causal structure of the black hole and what have you and so on, has made it possible for me to be influenced by infinity in a finite region, right? Infinity has suddenly become in my past, right? And this is exactly mathematically what this means. J minus a P intersect S closure non-compact. Non-compact, essentially, for the ones that aren't mathematicians in this room, non-compact just means big. And
is the PHI team also approaching the horizon?
So this is a conformal diagram where this is future time like infinity. They're not approaching, it looks like they are in the diagram, but they're flying as far away from the black hole as you like. It's just a conformal warping of the diagram makes it look like that. But they're, you know, they can always stay, this distance here can always be a megaparsec.
When you say infinite emails, what does that mean? We're sending them for all the time?
You're sending an email every day saying, Martin, where are you?
Yeah.
But and you're doing this forever, supposing you live forever. And because you're sending them towards the black hole, I'm receiving them. But my proper time from the moment I cross the event horizon to the moment I cross the Cauchy horizon is only 4 hours long. So in my 4 hours, I'm getting an infinite number of emails from you.
Okay. Doesn't sound right to me, but
It doesn't sound right to me either, but that's what the causal structure of a black hole does for you. That's what black holes do. That's what Kerr does.
Are you sure you receive those? Or because they also have different time, right?
No, I will perfectly happily receive them. Yeah.
where would you put them?
What's that? Where would I put them? Right. Well, they would all make my laptop explode, but I guess. But the point is that we can make the analogy a little less silly and just say, what about gravitational perturbation? Well, then if there's gravitational perturbation in and around the black hole, then these perturbations are being sent all over the place. Some are falling into the black hole, some are falling out. But the ones that fall in, there could be an infinite number of waves, if you like, being all focused and all intensified into a region along the Cauchy horizon. And so the intuition here is that, in fact, let's draw another picture, which is, let's draw another picture. The intuition is that if there's an infinite amount of energy, if you like, that's being sent in these waves along here, then something bad, some kind of blow up is going to happen in this region, blow up, right, of some magnitude, of some wave, some intensity, some energy, whatever. And that's going to basically destroy the space-time in this whole region. It's going to cause a singularity. And therefore, the space-time is going to close up. And there's not going to be a Cauchy horizon. And you're not going to be able to pass through the Cauchy horizon. And therefore, determinism is saved because now we have some initial data. Yeah, Richard, yeah.
Yeah, Martin. So the diagram or the Penrose diagram in the previous slide looked like it was compact, and so it looked like it was bounded, and it didn't look like there was a long enough world line for this email sender to send infinitely many emails at a finite rate.
That's just Shep's point, right? But actually, it's a conformal diagram, so the point is at infinity, so it's actually an infinitely long world line.
Okay, so and of course that may or may not be how our universe really is. It's just that universe that happens to have that property, that it's unbounded universe in the past.
Well, this is about the future, remember, but the real question is whether or not the Cauchy horizons within realistic black holes do in fact look like the ones I've drawn. Namely, are they like Kerr or Rice and Ostrom?
Okay.
Cool. So Garrosh and Horowitz put forward this kind of idea that basically, if there is a Cauchy horizon, then either this guy is non-compact, meaning you could have this kind of like signals from infinity reaching a point of the Cauchy horizon, or there's a kind of failure of strong causality. Okay, so now I'm going to show you some things which pour a little water on this picture. I'm not going to define to you what strong causality is, just take it for the sake of this talk that it just means the formation of almost closed causal curves. So they're not quite closed, it's not quite time machines, but they're arbitrarily close to being closed. Fair enough. So it turns out that if you look at Reistad-Nordstrom de Sitter, which has a Penrose diagram which looks like this. Right, and you look at initial data. This is now the Cauchy surface for at least that part of the space-time that is well, right, and then this is what's called the cosmological horizon, right, cosmological horizon. Then in fact, you see that Wald's conjecture is false because strong causality is preserved here. And if you take the past of this point and you take the closure of it with the initial data, then in fact it's compact. So that's just a comment that when lambda is positive, you can't possibly expect the previous statement to hold. This is something that was missed in the book, but I'm sure Robert Wald was aware of it. And so you could kind of just think, okay, well, let's forget about the particular statement of Wald and the Garrosh-Horowitz version of strong cosmic censorship in the context of lambda positive. Fair enough. Okay, that's just a small comment. And now the second comment is that, anything you do in mathematical GR is one of two things, unless you're studying the exact properties of a solution. One is a global viewpoint, where you study the very coarse global structure of a Lorentzian manifold, right? You study causality theory, you study the properties of light cones, the intersections of light cones with one another, etc. Right? You study these very coarse topological type things, okay? The other is the actual PDE world, right? So you actually do analysis, right? Where you have to pose initial data, control the initial data and whatever norms are relevant to the problem, produce solutions to this initial data, which are bounded in some norms relevant to the problem, show that existence holds for this solution, and so on and so forth. This you could call kind of the hard viewpoint. This is kind of a soft viewpoint. And by that, I mean that if you're working in B, your papers are basically more than 50 to 60 to 100 pages, 200 pages, 300 pages long, because you have to estimate all these things, and it's a very nasty, lengthy process. Whereas A tends to be very neat, very elegant, very quick. And so it's somehow soft, and it doesn't actually rely on the Einstein equations. It's more about the kind of the coarse global structure. And of course, you might say, from my point of view, for instance, I work in both the soft and the hard viewpoints. And what's particularly nice is that they talk to each other, right? And they're related, right? And the PDE viewpoint will end up producing spacetimes which have certain properties from the point of view of the global viewpoint. So some of them are globally hyperbolic, some of them produce Cauchy horizons, and so on and so forth. But something like global hyperbolicity or the existence of a Cauchy horizon or event horizon, these are completely coarse things that belong to point A. So you don't need to do PDEs to define these things or to study their properties. Okay, so these are the two approaches. And today, strong cosmic censorship is no longer viewed as some statement about whether or not the past of a point on the Cauchy horizon has non-compact intersection with the initial data or the failure of strong causality. Today, it's the field has gone into a direction where it's purely about PDEs, purely about analysis. And the question is, suppose you had generic initial data. Generic is a word to be made precise given the particular circumstances and assumptions of your problem. So it's a context-dependent term. That's a crucial point, by the way. If you had generic initial data, which means absent of symmetries, absent of fine-tuning, and so on and so forth, then the maximal Cauchy development, so that which you can recover uniquely from the Einstein equations on the basis of the initial data, should be star inextendable. Why do I write star inextendable? Because this star tells you what regularity, which for the purposes of this talk means what level of differentiability I can put on the metric and find extensions to the Cauchy development. You might say, what on earth is the relevance of regularity or differentiability in this context? It happens to be absolutely paramount because the ease with which you can extend a solution beyond its Cauchy horizon depends on what options you allow yourself. And what options you allow yourself is determined by what regularity class you're allowed to live in, right? So star and extendable, so, you know, it's very conceivable that the conjecture may be false for certain renditions of the word star. So if I demand lots of regularity, it's perfectly conceivable for the conjecture to be true for other types of star, right? So you shouldn't really think of it as a conjecture. You should think of it more of as a theme that has specific instantiations for each meaning of genericity, for each meaning of star. And you think of it as a spreadsheet. Strong cosmic censorship is not a conjecture, it's a spreadsheet. The y-axis is regularity, the x-axis is genericity, and you fill in the boxes, all right? That's how you can think of it kind of in the modern viewpoint. The reason why this modern viewpoint dominates or why these conjectures, you know, came to be is because if it was going to be a property of the Einstein equations, it better be done by solving the Einstein equations. And everything that came before this modern viewpoint was much more about the topology, the causal structure, and so on and so forth. So it's not actually about the Einstein equations, right? That's why things in terms of initial data now and Cauchy development. Initial data and Cauchy development means that you're only dealing with Einstein equations, right? Okay. So this is my comment about star and extendability. You know, if the regularity is allowed to be C0, which is mathematical jargon to mean continuous, then of course, you know, your extensions could be very, you know, could be very wild. And for the sake of the talk, I'd like to give you a little picture of what I mean by that. If you had a piece of paper, right, and I creased the piece of paper in the middle, this is a crease, then this region here, right, I can continuously extend it into this region, right? I can continuously extend it into region, but I cannot C1 extend it into region. So C0 is okay, but C1 is not okay, right? And C1 means that the derivative is continuous, and the derivative here is 0, and the derivative here is, say, 45 degrees or whatever. And you're seeing that if I map out the C1 you know, tangent of this plane, I get a jump. I go from 0 to something along the crease. And so it's C1 inextendable, but it's C0 extendable. So that's just giving you a flavor for what these regularity definitions mean and whether or not it's easy or not easy to extend beyond a Cauchy horizon. So if you allow yourself for C0, it means you can crease your space-time and you can make it rough. And if you can find these extensions, well, it's easier to find these extensions if you allow your things to be rough and you allow for creases. If you forbid creases, then of course it's harder to find extensions. And so the strongest possible version of strong cosmic censorship, you could argue, is the C0 version, where you say, even if I allow for creases, it's inextendable, okay? And that version happens to be false now, as of 2 or 3 years, okay? And that was a paper to Thermos Luke, yes.
Could you argue that it should at least be C2 just because, you know, you have to satisfy the field equations and they have second order derivatives? So
yeah, so you can define what's called a weak derivative, which in the field of PDE, I'm sure if you've done a PDE, I'm sure you're familiar with this. A weak derivative is something that where you don't actually have to be strongly differentiable, so you don't have to differentiate the metric, but you can come up with something that's a kind of weak version of an equation where you're integrating both sides and they still make sense as an equation. And when you do that, it turns out that you can still solve the Einstein equation. So you don't need C2 to solve it. So the actual currently most well-accepted version of strong cosmic censorship is locally square integrable Christoffel symbols, which is what you mean really, what your intuition was for C2. It's locally square integrable Christoffel symbols, because that's the level of differentiability where you can make of the Einstein equation, you can make sense of the Einstein equations from a PDE point of view. So yes, basically, yeah.
You should charge your computer.
Yeah, so I'm going to actually switch to fully computer in just a second, because so let me just see how much more of the yeah, so I had many slides. Okay, what is the best course of action now? Yeah, okay, let's do that. Okay, so I'll give you my iPad. and I'll carry on with the computer for now. So let me, thank you. Thanks. So let's see. Okay, so I'm going to share my screen and give you the slides. Okay, so we're back.
Let's see your Mac is standing.
Okay. Beautiful. Okay. So are there any questions at this stage? Are there any questions at this stage? Basically, the picture is, okay, so let's make it clearer. Can you see? Yeah. So the picture is this, right? Roger Penrose comes up with an intuition. This intuition is vague, it's not mathematics, it's just a vague intuition, but it is based on some calculations and some students of his that did some good work, et cetera, et cetera. And then mathematicians, some Lorentzian geometers, physicists, mathematicians come up with a kind of Lorentzian geometric version of the conjecture. But then PDE people, mathematicians later on say, well, actually, that's also not that great because we actually need a PDE conjecture to understand, to do something about the Einstein equations. And so strong cosmic censorship is now a problem about PDEs. Okay, so now I come to the point of what did we do? What is this talk about? So far, I've just given you a broad introduction about strong cosmic censorship. So what did we actually do?
Martin,
Yes.
You're talking about a Cauchy horizon here, right?
Yes.
What about real honest to God singularity? Is there an extension past that, or this theorem has nothing to say about that?
Yeah. Good. Okay, good. So if there is geodesic incompleteness, right? And you can extend past this singularity. Let's say you can extend it in a C11 or a C2 way. But you can do so in a way that preserves global hyperbolicity. So you can globally extend, like imagine you had Schwarzschild, but you can globally extend beyond the singularity. And you can't do this, by the way, but suppose you could. You can globally extend beyond the Schwarzschild singularity, but in a way that preserves the triangle, in a way that preserves this global hyperbolicity structure, right? Then strong cosmic censorship would still be true because there wouldn't be any Cauchy horizon. And so, in fact, from that point of view, strong cosmic censorship doesn't care about singularities. It only cares about whether or not you produce Cauchy horizons and whether or not they're extendable. So there is another direction, of course, which is that if your singularities are so strong that you can never extend beyond them, even as C0 way, which is particularly in the case of Schwarzschild, then you've already solved strong cosmic censorship, of course, because you can't extend anyway. So singularities are part of the picture, but they're not everything. And from the point of view of strong cosmic censorship, the only really thing that's important are Cauchy horizons and whether or not you can extend beyond. Good. So, okay, so what did we do? Well, what we did was this. I wanted to revisit some of the old ideas. I wanted to revisit some of the ideas of Wald, Gurish, Horowitz, Penrose, etc. I wanted to revisit them. And I had seen this paper that tried to prove the statement in Wald's book. Now there was I saw a mistake in that paper. The paper was published. It was announced as a theorem, etc., etc. I'm not going to name who it is, but I saw it was clearly wrong, and so I decided to try and prove it myself. And then I spoke to a person who, in my mind, is maybe the greatest Lorentzian geometer living today. A guy called Ethore Minguzzi in Florence, and my parents live in Florence now, and so I went to Florence and I visited Ethore and I told him, I think this conjecture is true. This is how I think we should prove it. I know you're an expert in C0 Lorentzian geometry. That's when the metric is allowed to be merely continuous. So all of the techniques that you see in the books, everything fails. Everything, you have to redesign everything, right? Geodesics don't exist. The push-up lemma doesn't exist. Oh, everything fails. So you have to come up with a new version of Lorentzian geometry that allows for these very, very rough metrics, which become interesting now because of the PDE picture, which tells you, careful, you have to think about low regularity now. And so Ethore and I spoke, and we started to try and prove the conjecture that was stated in Wald, right? And then we realized two things. First of all, the conjecture is false in Wald, right? Because of what I showed you before, the lambda. Lambda is positive. You can find something you can find extensions of Rice and Ostrom where it's compact, etc. But then we realized that behind Wald's conjecture is another statement which is true. And in particular, this statement isn't just true in the setting that Wald and Girosch-Horowitz originally intended it to be, namely at least C2. It's true in C0. So you can think of it as coarse. You can think of it as like, you know, as rough as you can be, as permissive mathematically as you can be, there is a true statement out there. And the statement is the following. By the way, what's the situation? It should work? Okay, great. Oh, okay, so you can.
That's my screen.
Okay, so I'm going to stop showing this one.
No, you've already stopped.
Oh, you've done it all. Oh, wow. So if I move this, is it? Oh, no.
Yeah.
Oh, is it moving? Oh, Jamie, thank you. I was getting stressed for a second. Good. So this is what we prove. You have a C0 space-time. So as permissive as you like. Okay. You have a partial Cauchy surface, initial data. You have a non-empty Cauchy horizon. So far the picture looks like this. You have initial data. You have a Cauchy horizon somewhere. You don't know where, but you have it somewhere. And then you zoom in, you take a point P on the Cauchy horizon. Okay. And then what you can show, so this is S. Okay. And then what we show is the following. We show that this guy is non-compact, or they're past imprisoned generators of H plus of S. I'm going to tell you what imprisoning means. The Lorentzian geometers have always had a vivid imagination to come up with their definitions. Imprison for the sake of making you laugh a little bit. I'm in prison. There's a null geodesic, so maybe a torch. Right, this is a torch in prison. No, I'm joking. What imprisoning means is that the past generators of the Cauchy horizon are past inextendable, so they're as long as you can be, but they happen to be living in a compact region. And what that means, so this was my past imprisonment. What that means is that essentially, you know, the Cauchy horizon must be kind of looping around in you know, because they're trapped in a compact region. So in a compact region. So what that means is that these generators must be kind of looping around somehow. Okay. So either this happens, or, so that's option B, or option A happens. And option A, you'll notice, is a slightly weaker conclusion than what was said before, namely J minus of P intersect S is non-compact. That means that if this is the initial data S, we take the future cone of S. Okay. We have some Cauchy horizon somewhere up in there. We have some, you know, this is a Cauchy horizon. We take the past of this point. So let me do a different color. Right. This is J minus of P. This is the point P. This is the Cauchy horizon, H plus of S. This is the initial data, S. Right, and what this means is that this region now, so this region, whatever it is, right? So now let's draw it by shading it in red, let us say. right? What this means is that the closure of this region, okay, is non-compact. So it's big. And if you recall the email scenario at the beginning of the talk, this non-compactness would mean that, you know, in the future of S, I could organize, say, a time-like trajectory that could send signals, right, for an infinite amount of time that could affect the point P. So in other words, the causal structure associated with the interior of black holes, Kerr or Rice and Nordstrom, is what you're seeing here. Those causal structures are exactly of the form where the set J minus P intersect J plus of S is non-compact. And so therefore, in principle, you could consider the organization of blow-up phenomena by exploiting the non-compactness of this region. Non-compactness, remember, meaning that this essentially just goes on forever. It's infinitely big. So that is, so remember, there are two forces at work in general relativity. There's the cause and there's the macro and the micro, a bit like economics, macroeconomics, microeconomics. Macro is this very cause topological, Lorentzian geometric, light cone structure, causal structure type stuff. Micro is details, PDEs, PDEs, PDEs. And these two things talk to each other, just like they do in economics. And from the point of view of strong cosmic censorship, it's now become a problem about microeconomics, namely about PDEs. But you can ask the question, what is the best you can do just from the macro picture, right? And so what's the most you can say? That's what I mean by the best you can do. What's the most you can say about these Cauchy horizons? And what you get is this. So you get essentially either there's a non-compactness of the form that you see in black hole interiors, or there's some causal strangeness. There's some past inextendable curves that are trapped in compact sets. And in the two families of solutions in general relativity that we have, where we have Cauchy horizons, could be the Taub-Nut examples, the Misner examples, the Kerr examples, the Rice and Nordstrom examples, they realize exactly one of the possible two choices. So it's either A or it's B. So this is a kind of, you can think of it as a structure theorem for Cauchy horizons, which is what was originally kind of put forward by Garrosh, Horowitz, Wald in the smooth setting. And what we do is prove a theorem, which is, of course, much greater applicability in terms of regularity, because it's C0, but the conclusions are slightly different. It's not that the intersection with the slice is non-compact, and it's not that strong causality fails, rather it's the following guy. B, by the way, is worse than the failure of strong causality. So B is a much more pathological occurrence than just strong causality failing. So in that sense, it's stronger than what was conjectured.
Which is the example that is B among the known solutions?
Taub-Nut, for instance.
Okay.
Taub-Nut, you see in Taub-Nut, what happens is, right, in Taub-Nut, let's ignore the title of this slide, but let's just do a Taub-Nut, right? So in Taub-Nut, you have something like this. And the light cone's tip, right? This is the future light cone, this is the past light cone, and then this is the Cauchy horizon. And you see that in this case, the horizons are actually even stronger than past and present. They're actually closed causal curves. But so long as they're lying in a compact set, right? So in this set here, then that would satisfy B. So a variation on Taub-Nut would be good. So that's okay. So I think we're in a good spot now. Let's see, what time is it? It's about okay. So let's have questions at this point, and then I can give you some last thoughts on what this suggests. Any questions at this point?
Does this like, I'm very unfamiliar with it, but does
No
this
worries.
like essentially solve cosmic censorship?
No, because strong cosmic censorship is no longer the problem that you saw in Ward's textbook. It solves the Ward textbook problem, sure, but it does not solve strong cosmic censorship, because strong cosmic censorship is no longer what you saw in Ward's textbook. Strong cosmic censorship is now about PDEs. However, it does do something which is interesting, right? What it does, from this point of view, is that you can now go back towards conjecture, right? You can say, okay, so when is it that this guy is non-compact? When is it that this guy's non-compact? And then let's specify, this is a black hole initiative, right? Black hole, let's specify to black holes. Let's just look at black holes. And then you can ask the question, suppose I have a complete future scry. Suppose I have an event horizon. Everybody in this room agrees that that's about as close to a black hole as we can get, right? Event horizons, future null, infinity. Suppose you have those in your space-time. Then what would you need to be true for Ward's conjecture to be true? Namely that this guy is non-compact. This is what you would need. You would need that J minus of H plus of S intersects every neighborhood of scry plus. Let me draw a picture. When there is a scry plus and there is an event horizon, we have something like this. Event horizon. Ramesh, I know you have to go, so please, I'll try and rush through this. Okay, so in Schwarzschild, what happens is that you have a space-like singularity like this, as you know. Okay, forget Schwarzschild for now. In Kerr or in Rice and Nordstrom, you have a Cauchy horizon, and then you can extend it beyond, right? You have an extension, this you know. The difference, right, between these pictures, let me now draw a different picture to you. Let me draw something that looks like this, but then you have a Cauchy horizon. So what does this look like to you? If I draw a point here and a past light cone here, and then I have the initial data here, S, then what do you see? Tell me what you see. What you see is something like this, right? This is now the past light cone of that point. Okay. Now, what do you see? Right? What do you see? What you see now is that for this guy, for this, what do you see? You see that J minus of P intersect S closure is compact. Right? So it's not, this doesn't satisfy plus, right? Where this is non-compact. Okay. So when you restrict to black holes, where there is a event horizon, future null infinity, when you restrict to black holes, whether or not this set is non-compact ends up being equivalent, we proved this by the way, ends up being equivalent to whether or not Cauchy horizons start here or whether they start inside. So you can then say, okay, let's make a PDE conjecture out of this. If I have complete generic initial data for the Einstein system, possibly with constant, possibly with matter, and if there's matter, sure enough, I can assume the matter's good, the matter's nice, the matter's beautiful, whatever. Then I look at the maximal Cauchy development of this, D of S, and I say this produces an event horizon. So we have a black hole, right? We have a black hole. Then if there is a C0 extension and a Cauchy horizon, then this guy is non-compact. And what this means is that essentially my Cauchy horizons start here. Cauchy horizons start here. They start here and not here. Okay. And what's nice about this is that this is now a PDE conjecture. Okay, so let me summarize what's been done. We took the Lorentzian geometric approach to strong cosmic censorship. We proved a theorem which proves what those conjectures were trying to do in a very, very low regularity class. Then from that point of view, we say, okay, how do we connect it with the PDE picture? Moreover, how do we connect it with the PDE picture in the context of black holes? And what we end up with is exactly this, namely a new conjecture, which you can study now from PDEs, so from the micro point of view, which says, if a Cauchy horizon form, it doesn't form in the deep interior of the black hole. It doesn't form in the deep interior of the black hole. It forms as close, right? It forms here. It forms so that the past of this point should cover the whole of the event horizon, the whole of the future portion of the event horizon. This is now a conjecture that you can study from the PDE point of view. So we've married the old and the new. Moreover, this conjecture is weaker than strong cosmic censorship. So it's not as ambitious as strong cosmic censorship, because strong cosmic censorship just says no Cauchy horizons. This says, okay, you can have a Cauchy horizon, but if you have a Cauchy horizon, it doesn't just form in the interior, it forms on the edge. At least it forms on the edge.
But didn't we always know that from a high A, when goes to 1, that the Cauchy horizon approaches the horizon?
Right?
In a spinning in a pure black hole,
Uh-huh.
as the spin goes up, the relationship of the Cauchy horizon and the horizon of the black hole approach one another.
No. Extremal black holes have Cauchy horizons, which look like this. The event horizon is like that. But even if what you were saying were true, that wouldn't matter, because we're doing generic initial data now. We're trying to figure out for most initial data, not something like a Kerr black hole, which is very, very specific, axisymmetric, stationary, and so on and so forth.
So Martin, I want to understand the C0.
Yeah.
Right? That's a statement about the metric, right?
Yeah.
So what is the statement for matter, T mu nu? What are its connection properties across this boundary?
Well, that could also be,
Not even C0?
well,
Correct?
yeah, that is correct, actually. Yeah, that's
Right.
correct. Yeah.
So you can really have discontinuities. in
Yeah. Yeah, you can have
multiple
shocks.
Shocks, exactly.
Shocks, yeah.
That's what I was thinking.
Yeah.
Okay.
Yeah.
Great.
I want to follow up on that.
Yeah.
When I think of this work, I think of the formation of black holes and the formation of horizons that can happen very, very quickly or almost instantaneously. And does this govern where the horizon is at any given time? So as the black hole evolves?
Yeah, exactly. So okay, so first of all, in your words, in your sentences, you must distinguish between what you mean by Cauchy horizon and event horizon. They're two different things, right? The event horizon is what's the boundary between the inside and the outside. The Cauchy horizon is the boundary between, is already inside the black hole, and it's the boundary between what you can determine from the initial data and what you do not determine from the initial data. So these two horizons are different things. But what this conjecture will, this work basically, settles an old statement in the field, but then it also does this new thing, which is it says, well, actually, let's just take black holes, let's just take Cauchy horizons, so these kinds of horizons, not these ones, okay, not these ones. And then it says, insofar as these ones are concerned, they shouldn't just form in the deep interior, right? So that you shouldn't have something like this. You should have something where this is future null scry and this is the event horizon. This picture should not happen. So should not happen, right? That's what the conjecture says. Right, that's what the conjecture says. And the nice thing about this conjecture, by the way, is that you can actually now study it from the PDE point of view. Moreover, to my knowledge, every PDE study of strong cosmic censorship that I'm aware of satisfies this conjecture. So whenever there's a Cauchy horizon, it always hugs future non-infinity. Namely, it's always out here and not just inside, deep inside. That's it. Thank you. Thank you.
Another question here.
Yeah, Richard, yeah.
Yeah, thanks. Excellent talk again. And I'm wondering, are the light cones oriented in these plus and minus 45-degree cone shapes based on the content of the space-time and the state of motion of the observers? So if that's the case, then these conclusions about where Cauchy horizons occur would depend on the content of space-time. If there were some space-times that would tilt these light curves due to their content, then these conclusions might not be robust to that.
Right, so everything we're saying is somehow observer independent, and everything we're saying is really just about the causal structure of the horizons with respect to the event horizons. And these are all intrinsic things that you can define and that will look very different depending on the space-time in question, but they're always, they're intrinsically defined, and in a sense, they're well defined. They don't have this problem of, whether or not in one space-time they look like that or like this. They're very intrinsic. They're very robust, if you like.
Well, I was talking about whether the actual orientation of those cones that look like those past light cones, if those would be tilted, like I think in the diagram of that cylinder that you showed, you actually showed light cones being tilted.
Yeah.
Yeah. So if these light cones can actually be tilted, wouldn't that actually affect where the location of the Cauchy horizons are?
Yeah, but you see, the Cauchy horizon is precisely the boundary where is the tilting of this diagram, right? Tells you that in this case, the Cauchy horizon is actually this line. So in that sense, the Cauchy horizon follows the tilting of the light cones. When I draw the black hole picture, the Cauchy horizon is like here. But in this picture, the Cauchy horizon is actually a line. So I go from 45-degree angle to horizontal thing. So in a way, there's no real issue here, because the Cauchy horizon is just what it will be, and that will follow the light. That will be determined by which way the light cones are tilting.
Exactly. So this the stuff that bends these light cones is also what might deform the Cauchy horizon.
Well, the Cauchy horizon just is the result of the deformation of what happens in the space-time.
Yeah. Okay.
Any other questions? Yeah. 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 Yeah, that's absolutely fine. Very, very good point. So, I drew it like this, and I said this doesn't happen, but I could have very well drawn it like this and said this doesn't happen. Or in fact, if this happens, and then this is a Cauchy horizon, that satisfies the conjecture. That is allowed, right? Because in that case, the past, if this is the event horizon, then the past, right, the time-like curves, their intersection with the event horizon is going to cover the whole future portion of the event horizon, and therefore it's non-compact. So this is allowed. So I guess my language, deep interior, is to be taken with a pinch of salt. Say again. Yes. Yeah. So I'm in the setting of black holes where I have a scry and event horizon. And so from that point of view, you could say, oh, you're already in a setting where you've developed a complete future scry and event horizon. So you're kind of already assuming weak cosmic censorship. Yes.
All right, so we should probably wrap it up. Let's give another round of applause.
Thank you.
We'll see you in a week.
Jamie, thank you.
Great.
No problem.